Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors 6-3 Part 2 homework solutions on applications of vectors. On this problem, we're trying to combine these three vectors that are all three-dimensional. So we're just going to go through and figure out what's happening with the x, y, and z values independently of each other. So for x's, we've got 14 minus 7 minus 3. This is just all the x values together. Now for the y values, we've got 2 plus 9 minus negative 8, so plus 8. And then finally for these z values, we've got negative 6 minus 4 and then minus negative 18, so plus 18. Let's go through and calculate each of these. So 14 minus 7 is 7, minus another 3 brings us to 4. That's the x value. For the y value, we've got 19 if we add these three together. And for the z value, this is negative 10 plus 18, so 8. On this problem, we're trying to do a dot product with three-dimensional vectors. Before we do the dot product part, I'm just going to distribute this 3 in the beginning. So that's going to give us 6, 21, 3, and we're still multiplying by this other vector here. So to dot multiply, let's multiply the x's together, so 6 times negative 5. And to that, we are going to add 21 times 11, the product of the y values. And then we've got 3 times negative 4 also getting added in there. So this is going to be negative 30, and then this one here, well, 21 times 10 would be 210, plus another 21 brings us to 231, and over here this is negative 12. Negative 30 plus 231 gives us 201, minus 12 is going to be 189. On this problem, I'm trying to find the magnitude or absolute value of this three-dimensional vector. I'm going to do what I do with 2D vectors, essentially just square everything in here, add it all together, and then square root the sum. So we've got the square root of 4 squared plus negative 1 squared plus negative 9 squared. This is the square root of 16 plus 1 plus 89, or 81 rather, 81. Then we've got, 17 plus 81 gives us 98. Now 98, you might remember, this is really 2 times 49. We can square root that 49 to get a 7 radical 2 for our final answer. For this problem, we're trying to do a dot product, but there's also this multiplication by 5 in here. So I'm going to distribute this 5 first, just so I don't have to mess around with it. So this first vector is staying the same, but the second vector now, I'm going to distribute this 5 to each of these coordinates. So we've got 20, comma, negative 45, comma, negative 10. Now I'll do my dot product. So I've got negative 3 times 20 plus, now the y values get multiplied, 4 times negative 45 plus negative 8 times negative 10. So that's negative 60, this is negative 180, this is positive 80. And let's see here, I know we've got negative 240 for those first two terms. Add 80, that's going to be negative 160 altogether. For this one, we're trying to find the magnitude of a three-dimensional vector. So we're basically just going to square all of these, add them together, and square root the whole thing. So square root of 9 squared plus 2 squared plus negative 6 squared. That's the square root of 81 plus 4 plus 36. Let's see now. 81 plus 40, if I combine these, that's 121. And the square root of 121 is actually exactly 11. For this problem, I want the magnitude of this three-dimensional vector. So I basically have to square all these, add them together, and square root it. So square root of 8 squared plus negative 2 squared plus 2 squared. That's the square root of 64 plus 4, which is going to be the square root of 72. Now I can simplify this radical. 72 is really 36 times 2. So square root that 36, and we have a 6 radical 2 for our final answer. For this problem, we're going to follow the rules of two-dimensional vectors just with an extra dimension. So using PEMDAS, we're going to start by distributing this 3 to the first vector. That gives us negative 3, comma 12, comma 30, and we still have the second vector untouched. Now we're going to just add the x, y, and z values separately. So we've got negative 3 plus 5, giving us 2 for that first coordinate. And then we have 12 plus 15 for 27. And finally, 30 plus negative 8 gives us 22. For this problem, we have not one, not two, but three vectors, each with 3 coordinates in them. So we're just going to go through and do everything independently with the x values, y values, and z values. So writing a new kind of super vector here, we've got -10, -5, plus 13. All of that is just giving us the new x value. Then for the y values, we have 20 minus -6, so plus 6, and then plus an additional 2 here. And then comma, we have the z values, 4 minus 8 plus -1 or -1. All right, so going through and crunching the numbers, this is going to be, let's see, -15 plus 13 is -2. Over here, we've got 28 for the y value. And for the z value, 4 minus 8 is -4, minus another 1 is -5. On this problem, we're trying to find the dot product of two 3-dimensional vectors. So we're going to just take the products of the x, y, and z values independently and then add them all together. So we've got -3 times 10, -5 times 4, that's getting added in there, plus 9 times 6. So let's see here. This is -30 plus -20 plus 54. -50 plus 54 is just 4.